Give a big welcome to our speaker, Khai Pham, on From Machine Learning to Machine Reasoning.
Hi, everybody. Good morning. Very happy to be here. My first time at Scale, and had already a great experience yesterday. In addition to my company, Thinking Note, I'm on the board of Khai. We had a Khai Summit yesterday. Reza, the chairman, is here. We had a fantastic session. Before I start too, I would like to thank you, partner, Arcus Nexus. CEO of Arcus Nexus is here. Amazing company, 300 people, IT, and very talented people to work with us.
We'll get the volume up a little bit.
Okay. Well, I think I have to make it louder. There's no volume. Okay, I'm going to try to talk louder. Is it okay now? Okay. So, of course, we are about AI. And the way I started, I would like you to think a little bit what we are talking about. Because right now, people talk a lot about AI, but I'm not sure everybody understands the same thing. So, intelligence, right? Because we talk about artificial intelligence. The most powerful way that intelligence exists today is in human being. Right? So I have a question for you. What human intelligence we are using as an input? I say input because we are here in the tech environment, so you used to see input and output, right? So what do you think the input of intelligence? Okay, so knowledge. But why, most of the time when you go to AI conference, people never talk about knowledge. They talk about data. Okay? The second thing is then, okay, but why intelligence use knowledge to do what? Reasoning. But why, again, when you go to most of the AI company, people don't talk about reasoning, and they talk about pattern recognition. Okay? Amazing what we can do today with pattern recognition at scale. But wait a minute, what we can do with reasoning at scale. So, as I mentioned, so I'm founder CEO of Thinking Note. What we do is we use distributed reasoning AI to build digital cell clones. As you know, any major industry, aviation, automobile, you use simulation, right? You have a digital model before you do anything else. We don't have that in biology and in pharma. So what we do is we use our AI technology. We take the gene expression data of the cell, we inject it into our human cell foundation model, and then we let it differentiate it as a stem cell would differentiate it, you know, into muscle, into bones, into cancer, into inflammation. So about myself, my background, I have an MD and PhD in AI at Sorbonne University. It's why maybe you hear my French accent. Yesterday, Pankaj was talking about the history of AI, and it started about 70 years ago. On these 70 years, I did 30 of them. So I see a lot of different type of AI and how and where we can go today. So I had my first AI company. It was in fintech CRM in Silicon Valley. It was very successful. But my heart is in life science. What can be more interesting than working on life? And I believe that the biggest impact of AI for this century is biology. So, intelligence. Well, there are a bunch of definitions, but this is the one that I like, from Jean Piaget. L'intelligence, ce n'est pas ce que l'on sait, c'est ce qu'on fait quand on ne sait pas. So, intelligence is not what one knows, it's what one does when one doesn't know. So when you think about it, right, the existing AI system that we talk most of the time, does that fit to this definition? But I would add something. When one does something, but with rational outcome, because yeah, you can do a bunch of things that you don't know, but we can have hallucination. So AI ML, each time I see that, it's kind of irritating me because either we decided to separate the two things or we put them together, because each time we talk about AI/ML, it's about ML. And don't make me wrong, I'm not against ML. I did that, and it's amazing. It's going to continue to grow amazingly. But we have to understand what is for what in terms of use. So you have two main cognitive kingdoms, pattern recognition and reasoning. I have a fantastic Chihuahua. I love her very much. But what she does is mainly pattern recognition. You know Pavlov, right? Ring the bell, the dogs right away have saliva. It's pattern recognition. On the other side, reasoning. Of course, you all know what is reasoning. By the way, what is reasoning? So we do that every day, and we don't even pay attention. So we'll see about that. So there is a book, very interesting book, study on animal intelligence and human intelligence. It's Professor at Stockholm, Stefano Ghirlanda. He's now part of our team. It's a very interesting comparison because it fits with what happened today, machine learning and AI or reasoning. On the psychology point of view, I'm sure a bunch of you have read this book, Daniel Kahneman, System 1, System 2, fast, slow, reactive, reflective, associative, logical, unconscious, conscious. Per day, you do about 30,000 decisions. I don't think you are conscious about it, right? You take your phone, how many times you take your text, you don't even think you do it. You open the door, and so on and so on. So 95% of your decision per day is completely unconscious. 5% is conscious. Why? It's painful. It's better to do things automatically than to have to think and to reason, right? So from there, we have two main AI schools. Pattern recognition, and both schools started at the same time, as you know, in the 50s. But one say, okay, to reproduce intelligence, we have to reproduce the neurons, because apparently it's your neuron. So it's a physicalist school. And it's what you hear today about artificial neural networks. But I don't really like this term. I prefer connectionism, because a lot of artificial neural networks has absolutely nothing to do on how a neuron is working. Excitation threshold, refractory period, and so on is not implemented. On the other side, it's a symbolic school where the term AI has been coined. Computational logic, of course. So on one side, data-driven, on the other side, knowledge-driven. Correlations, causation. So these two things are super important. But all the time, I don't know what happened in our human brain, we have tough time to dissociate it. We all know it, but we still consider correlation as causation. So a second book, if you didn't read it, please do it. Joe Dapper, I mean, he's my mentor, fantastic, probabilistic network and so on, really explained that very well in his book of Why. So I'm going to illustrate one of the way to do reasoning, one of the way. Okay. Here you have the lady and the tiger. It's a puzzle. And you have to infer where's the lady, in room 1 or in room 2. For that, you have some knowledge. So if the lady is room 1, then the sign 1 is true. If the tiger is in room 1, the sign 1 is false. If the lady is room 2, then the sign 2 is false. If the tiger is in room 2, then the sign 2 is true. Sign 1, both rooms contain the lady. Sign 2, both rooms contain the lady. I'm sure maybe you feel like, each time I added some knowledge, it's not painful, but you have to pay more and more attention, right? Well, based on Miller, we can only process 5 to 9 concepts at the same time. But what it illustrates here, if you spend some time, you are going to infer where the lady should be. Any idea? Yep. Room 1. Nobody else? Okay. So how human we do that? We start with an assumption, right? So let's suppose that the lady is in the room 1. It means that the sign 1 is true. Let's go to see the sign 1. The sign 1 say both rooms contain the ladies. You cannot. So then I'm going to challenge that. Okay, so now let's suppose the tiger is in room 1. Then the sign 1 is false. Oh, okay. The tiger should be in room 1 because sign 1 is false. So it's not just you. I did this test several times. And human, we are easily confused. Even we are super smart, it's not the issue. We are easily confused. 2 things here. Nothing to do with data, right? No data here. 2, you can infer new knowledge from existing knowledge. This is very important. Now, if you infer correctly, it's in room 2. So I try on ChatGPT. I try on ChatGPT 3.5, 4, BART. Either I have the wrong answer with the right explanation, or I have the wrong explanation and the right answer, or I can have both wrong. And so you don't even know. So we will get to that. Again, I'm not against it, but I just want you to know what to expect for what you have. Don't dream about AGI or what kind of these things for now, even though we don't even know if it's interesting. Now let's go to 9 room. Jeez, right? So one of the way that reasoning AI, yep. Sorry? Exactly. So the reasoning is capable of challenging your assumption. Does machine learning challenge your data? Okay. Because it doesn't have reasoning. But again, amazing for a number of pattern recognition things. So let's take an example. Yes, if you want to recognize image and so on, this is fantastic. Don't even try reasoning, right? You just train, you do it. So this is an example. But now let's take another example. Let's suppose you want to be able not only to predict polio outbreak, but how to stop it. Okay, if you have a lot of input and a lot of case, statistically, you can predict polio outbreak based on all these things, right? But you still don't know how to stop it because you don't have the causation. Right? On the other side, if you have the causal model or the mental model, then you understand what's going on, you can predict by deduction, and then you can intervene. Why all of us, we spend so much time either at school, at training, and so on, is to build the mental model, is to build the reasoning model, is to go after the causal model, which is science. Okay? So correlation help you to have some clue, but the goal is causation. Now, in some approach, people talk about causal machine learning using real-world data. The answer is no. You cannot have causation by just observing real-world data. You need either experimental data where you knock down one thing and see what's going on, or you have to have knowledge to be able to do that. So now you know how to stop it. But more importantly, let's suppose in your input data there is something that has nothing to do with the output, right? But you don't know it. So in this case, ice cream. Well, we know that during the summer, people eat more ice cream, and during the summer, people gather more for barbecues and so on, so the virus spread out even more. So yeah, ice cream is completely correlated to the polio outbreak. And at that time, physicians even advised to eat less ice cream. Okay? So please, each time you use only statistic without the knowledge, you're going to eat a lot of ice cream. Yeah. So, yeah, correlation, causation, we all, abuse, right? Statistic 101, correlation is not causation. But does any causation have to be correlated? Yes, no, maybe. Well, of course, if I ask you a question, it's something behind. Well, some causation do not have correlation. How's that? It's not related to the causation itself. It's related to your data. So if you collect data and you see that each time that it rains, the crop is growing, right? So then you say, oh, it's correlated? Perfect. And yeah, it should cause that. But as you know, if you have too much rain, the crop dies. So if you have all this data, sometimes you see it grow, sometimes you see it die, your correlation is 0. So correlation, causation is very tricky, it's very profound. And actually, even challenge causation. Does that exist really? Or it's just an illusion or just a mind-building concept? But we are not going to go there today. So today, we are in the correlation era, right? But I really want you to do not forget the goal. Why do we process data? Is to have knowledge. Right? And if there is one thing you remember of this presentation, is the following. Knowledge is the smartest and impactful way to compress data. It's the reason why we are where we are, what we can do, and so on. So each time you work at the knowledge level, you are going to save a lot of data challenge, computational challenge, accuracy challenge. But of course, data is not perfect. Knowledge is not perfect, neither data. But it's how incrementally we build things. Right? So, but the problem is, the available knowledge is completely useless. How many books you have in the library? And, well, it's because somebody have to acquire the knowledge, so then it can apply the reasoning. So the bottleneck, as you can see, is at the knowledge acquisition for the reasoning. And then, with more and more technology that we have today, we increase the knowledge. And a lot of people continue to work on data, which is essential. But wait a minute, we have now the knowledge bottleneck. And trust me, connecting the dot at the knowledge level will be way more productive than trying to extract something from scratch with the data. So this is where knowledge-driven AI come in. But why you don't hear much about it? Well, it's because the different system, and I will talk about it rapidly, most of the time, people were thinking about how I can build a formal system, and then to see how I can fit into this formal system, how we reason. So usually it's centralized system. For example, you can have rule-based system and so on, that I'm sure a bunch of you know about it. Once you have a centralized system, you can process knowledge only in the one way. The thing is, knowledge is diverse, and it has different type of reasoning. You do all that all the time. You go from analogy, constraint, case-based reasoning, logic, and so on in your mind, no problem. So if you have one engine, it cannot make that. So the work that I've done for 30 years is based on distributed AI, where each piece of knowledge itself is the reasoning engine. a mini reasoning engine, which means there is no more separation between knowledge and reasoning engine. And I don't think in our brain we have one side the inference engine and on the other side the knowledge, right? So this have a consequence on what type of generative AI you end up. So as you know, on the left side, this is the generative AI you know today, and it generates pattern recognition, right? And generate text, image, or video. On the other side, we use distributed reasoning AI to have generative AI. And instead of generating text, image, or video, we generate reasoning model, the mental model, the way that, how we understand the world. And we use that in drug R&D. So people are working on designing the drug, but as you know, a drug by itself, who cares? What matters is the impact of the drug on the cell. So we use our AI to generate digital cell clones, the human digital cell clones. So then we can simulate the impact of the drug on the cell. So large language model, you have to understand something else. Again, it provides amazing opportunity, but you have to really understand what it does exactly. Large language model is mainly about helping you to have an input to the system and does amazing output to the system with natural language. The issue is it doesn't have the reasoning model. It doesn't have the internal representation of the world. And I'm going to give you a clue why it's of use. How many times you are looking for a word to express what you mean? Which means that your mental model is not just based on word. Otherwise, you would give me right away. You never hesitate, right? I want to say something. The thing is, large language model is one of our mental model. Drawing, music, dance, mathematics, science, body language, and reasoning model. So I did a kind of introduction on machine learning, reasoning, and I would get back to the end because I have an open question to that. Now let's see how we really apply that to life science. So definition, because human, we need that. AI digital biology, it's what I define. I don't consider it perfect or complete, but it's the way I see it. It's a multidisciplinary field using AI as a main framework to understand first, to simulate natural biological events, and to design synthetic biological entities. Okay? Human, once we understand something, we always want to create something new. So why so important? Just to give you the level of investment, right? This is 2023, $60 billion just in AI drug R&D, and it was before the end of 2023. There is about 800 AI drug R&D company. But like I said, we just don't do drug, we do the cell. So why so important? It's because if you are not in the field, you probably heard about it, right? Developing a drug costs money. Well, it takes about 10 years. You have 4% chance of success, and it costs average $2.6 billion. So accelerating any of this phase is very important. It's why $10 billion have been injected for machine learning in drug discovery. But like I mentioned, having a drug is not enough. What matters is the interaction with the cell. And it's why it takes so many time to test on the cell, to test on the mouse, to test on humans. So what if we can simulate that from the very beginning, at every of these stage? First of all, we can save a lot of mice. And I'm serious about it. It's not just a joke. I mean, it's terrible to inject to some living being that has no problem and injected cancer, inflammation, whatever. So the way that scientists today are thinking to develop drug and so on is using pathways. So pathways in biochemical world is to know, okay, this molecule with this molecule have this reaction that produce this, and this. So if I block this molecule, then I block this reaction, so then this, and this. Because at the end of the day, your cell is about the result of how your cell produce different protein and other molecules, right? The thing is, again, human, we can only process 5 to 9 concepts at the same time. So this is very poor. Very poor because this is much more complex at the cellular level. And what I show to you is a simplistic way to represent the cell. There is about 1 billion biochemical reactions per second in the cell. This is part of the knowledge we know. But the problem is you have all the interaction between all this knowledge. So no human is even close to that. So what we do is to use reasoning AI to model that and to do simulation. Okay. So from this, we can have a better understanding of the disease. So let's dig a little bit deeper. How do we do it? So we have created a human cell reasoning foundation model. For that, we gather the knowledge, because one another important limitation of reasoning AI is before you reason, you have to have knowledge, which is knowledge acquisition. So you have 2 ways to have knowledge acquisition. One is you interact with the expert directly, and then you can understand what's going on, and then you can put it into the machine. It's a long and tough process, but sometimes you have to do it. In this case, actually, we are lucky. There are a lot of database on biochemical reactions and so on. Our network, for example, has about 150,000 nodes, where each node is a proteins, regulator, catalyst, reactions, and so on. Right. So once you have this human cell reasoning foundation model, it's a kind of stem cell in the sense that based on the gene expression, it's going to differentiate it. As you know, all your cells have exactly the same genome, but what matters is the gene expression of that cell, which become a bone, a muscle, a cancer cell, inflammation, and so on. So we use the same approach to generate digital cell clone, the digital cell differentiation. And it takes us today actually less than 2 hours, just about 1 hour. Then we can do all this stuff in drug R&D. So let's now go a little bit deeper to understand how it works. Connecting the gene expression to the phenotype of the cell. The phenotype of the cell, you can see it as the state of the cell, right? So you want to understand what's going on. So using machine learning and GWAS has provided a lot of information. It has been worldwide work, but it's still correlation, which means you can have gene association. And as you know, in statistics, you can have a lot of false positive, like the ice cream, and you still don't really understand what's going on inside of the cell. On the other side, you can have gene interaction. And what you are looking for is interaction understanding, not just association. And you can do that because all the feedback loop in the cell and so on can allow us to understand. So now one thing very important to see as well. When you take the gene expression of the cell, it's the photo of the cell at that moment, right? You don't know what is going to go after 5 seconds, 1 hour, and so on. It's just a photo. Exactly as in Gen AI, where you take a photo and it generates a video. It's what we do. We take the gene expression data, and then we generate the movie, but based on reasoning. We generate what it can be a T+1, T+2, etc. Of course, it's an approximation, but it's way, way, way better than any human we can infer. And this allows us, once you have the dynamic, you can understand causality. Because causality doesn't exist without dynamic. So these are real-world data. This is one of the protein. There are 15,000 of them functioning at the same time. The two dots here are at the beginning when you measure the gene expression, so the sick one and the healthy one. And this is the data you have, that's it. Well, with our reasoning engine, all these dots are generated by the reasoning. It doesn't exist in the data. So first of all, you can see the dynamic. Oh, there is a peak. So then why it's interesting? You can regroup all the proteins that have a peak at the same time, which means they probably interact to each other, right? The second thing is, as you can see at the beginning, the sick is higher than the healthy one, right? But if you see the evolution, the sick become lower, something you don't have in the data, just because you took the photo of the cell at the moment that it was higher, right? And then another benefit is we generate about 50 million additional data points per digital cell clone. So people say, data in life science, it's enormous. We want to make it very worst. Sorry, a lot of data still. So all models are wrong, but some are useful. I'm sure a bunch of you know this quote. I love it, and it's perfectly applying here. So we did that for cancer. This is about predicting the drug response to a very strong inhibitor for cancer. So it's very important to predict drug cancer response. So then you can, select the patients and so on, right? In this case, our customers say, okay, don't even try. And they try machine learning and so on. They didn't get anything really, because the data set was small and cancer is very heterogeneous. It's not like one cell is exactly that, it's a mess. We were able to have 89% correct prediction. But you start to understand why. Because we generate 50 million additional data points. Okay? Here, autoimmune. People, for example, have inflammatory bowel disease, but actually any autoimmune where your immune system become crazy and fight against you. So we simulate what happened to the macrophage, we simulate what you would do in wet lab, we simulate the drug, and this is the rate of success we had. Then we validate on the target and so on. And then our last customer, we were able to identify a new target for people who are resistant to anti-TNF, which is a super powerful anti-inflammatory drug for IBD in 4 months. Usually, these things take years. So this is the size of the data. The last one, we only have 10 patients, 5 fully response and 5 partially response. We can do that because it's not statistic. Right? So, but again, because sometimes people think that I'm against machine learning. No, there is another species in AI, and then another one that I will conclude that you have to have in mind. So yeah, we have a partnership with pharma and so on. Okay, so my talk, if you remember the beginning, it's about from machine learning to machine reasoning, right? Now, yeah, neural networks, right, for machine learning. But wait a minute, neural network is not the only way to do machine learning. Okay, you have decision tree, you have instance-based, k-nearest neighborhood, this kind of things. Then, yeah, machine learning is not the only approach in AI. You have the symbolic AI, you have nature-inspired AI, and you have multi-agent AI. So the 30 years that I spent was about how to unify that. So I went across all of them, most of them, implement a lot of them to really understand which one bring what and how they should interact. So I'm going to go a little bit more on the symbolic AI since we talk about reasoning. Production rules, I'm sure you heard about it. expert system, if A and B, then C. DeepMind has announced like a month ago something that combining rule-based system with large language model, they just have an amazing breakthrough of solving some mathematical problem. But trust me, rule-based system is super basic in reasoning. We don't have time to get into that, but then you have constrained programming, where you just describe the constraint to the system and you let it evolve until it satisfies all the constraints. Then you have the natural language programming, which is not the ChatGPT. This is with Noam Chomsky and so on. It's a very explicit way to try to understand a sentence. So it provides amazing results on programming language and so on, but it has failed on what ChatGPT was able to accomplish with the statistical approach. But it's super more precise than ChatGPT. So I can see you coming. Why don't we combine them, right? Then case-based reasoning. A lot of time, you think about the problem. Oh, this reminds me of a problem that I had, right? Then you have semantic network, how you connect different nodes with some meaningful relationship. Then logic programming, Prolog was amazing language for that. I mean, I don't know if some of you have used it. Planning and scheduling, then frames and other things. So there are so many research going on, thinking about new system and so on, and it takes a lot of time to get mature. So the second part that I want to focus on the multi-agent. So the first one is message system. So all of us, we can be an intelligent agent. And let's suppose I need water and I don't have water. I can send a message to somebody that I think know where's the water. So messaging. The other one is, okay, too many people. I don't really know people. I'm just right on the board. I need water. Who can help me? And then maybe someone will tell me, okay, I can do it. The issue with that, first of all, the benefit, it distributed completely the AI to solve the problem. Each agent has a specialties and collaborate to solve the problem, rather than to have a centralized system. The issue is, let's suppose I'm agent A. I'm the one that needs water. But at some point, I don't need water anymore. But if I don't tell or I don't erase things, other people already looking for water, and then the water maybe need another thing, and so on. So, and the system become completely chaotic. So the macro connection is, we are going to talk about that. So from machine learning to machine reasoning, what about unifying it, integrating it, right? And this is what people call today neuro-symbolic AI. So how to combine pattern recognition with reasoning. And the main way to do it today is to connect statistical system, machine learning, and symbolic system, and have a bridge. Can we do better? What about, this is the two schools we have. What about to have a unified AI framework, where you have the same structure, the same basic component that can do both? So this is what I'm working for 30 years. This is publication 30 years ago. And I didn't want to publish too much because I went to building companies, because I thought it's the faster way to grow, to show that it works, and not just spend time arguing with a bunch of people. So my first company was very successful for fintech CRM, and right now we are in the pharma. So the macro connectionism, the term, right? If you remember at the beginning, I was saying to you, artificial neural networks, the real term that people use in the field is connectionism. So what is macro connectionism? Is that in connectionism, the basic entity is the neurons. In macro connectionism, I was thinking, you know what? The neuron maybe is not the right level. It's super great level to recognize a cat, to do pattern recognition. But to do reasoning, maybe the right level is a set of neurons, assemblies of neurons. So macro-connectionism is about using assemblies of neurons to represent reasoning, knowledge, and so on. And at the same time, because it's connectionism, you can have the benefit of connections. So I call that May I, and it's a unified AI. So I have a message here, is that, until now I was focusing on working this different company, life science and so on. And I realized that the technology now is mature to open it. So any of you is interested to work on AI or unified AI, please contact me. I'm on LinkedIn. I have no idea how this is going to go, work, organize, but it's just from my heart, I think that it's the right time to share that with the community, and it's why we're quiet as well. So this is my whole talk, and I have a little bit time for some question. Thank you very much.
So thanks. That was a fantastic talk. I really enjoyed that. So yeah, we do have time for plenty of questions. So if you can raise your hand, I'll try to make sure everybody gets a chance to ask what they want to ask. I think, there we go.
Hi, impressive talk. I have a background in biology, but also in computer science, so a lot of it makes a lot of sense to me. Given your unified AI approach here, where do you think this will be first applied outside of the life sciences? Where do you see it, like the natural spot where you drop this in and you can start training it, which is not going to be a trivial exercise?
Thank you for asking the question, because one of the reasons why I was asking for you to gather is to have this kind of question. If I would go is, of course, healthcare is close to, biology and life science. But I would say domain where you have deep expertise. And you need different type of expertise to combine together. It's why, for example, I'm not interested in AGI, and I think we are far from it anyway, but I'm interested in super intelligence network. Expertise connected all together. So I don't have the exact answer to you, but it's about, where you have most of the knowledge and how you can leverage and trying to connect the dot in this domain.
I'm curious more about how the biochemical pathways map you showed is playing into your simulations. Do you actually have all those coefficients for all those reactions in a model that you're then driving with inputs from machine learning? I don't quite understand how you're actually doing the simulation. Is it equations governing all those biochemical pathways actually in the simulation?
So as you see, the concept of machine learning is so deep in us. So we are doing machine reasoning, first of all. The other thing is, yes, some people have tried to put the equation, ordinary differential equation for each thing, and it went nowhere. But how the scientists, we solve the problem? Go back to how human we solve the problem. Do you think that each time a scientist think about a new target and so on, think about differential? No, it think about some knowledge level first, and then you can dig deeper. It's what we do. We take the knowledge at different level of abstraction, when we have a very deep knowledge, then we put it, but if we don't, we are at a high level. So we use exactly the way that we are capable of overlapping some place where we have not a very granular knowledge by another level of abstraction of knowledge. So we don't use all the pharmacokinetics for everything. It's a combination. Yeah.
I was wondering if you were familiar with retrieval augmented generation, RAG?
RAG?
Yeah.
Yeah.
And can you compare and contrast? Like, my understanding of RAG is that, you're trying to take the LLM and then kind of bolt on a knowledge graph to try and give it a little bit more, I think, grounding, like you're saying, of the causal element.
Yeah. So RAG is very interesting, but it's very simplistic. It's just about pointing on some content. Okay. I cannot say that in public, so if you're interested, I have a story about it that I did 10 years ago, but it still doesn't provide you any reasoning. It just gives you the source of the information in a better way. Yeah.
Absolutely fantastic presentation. I think, that gentleman asked about what are some other domains, and I think a lot about what I do for a living with sort of communities, mostly around businesses and organizations, and, like the tragedy of commons from Garrick Hardin. Like, it just seems like there'd be, I don't know if I'm ever smart enough to take what you're doing, but to me that would be an incredible way to take sort of excuse the phrase, but biology of how organizations work. And we have tons of knowledge from Peter Senge to just a wealth of knowledge. I'm just wondering, like, where would one even start? Because it just seems like that would be a domain. I mean, it wouldn't cure cancer, but boy, it could help organizations.
Yeah, no, absolutely. It's why, we focus on life science today. But just imagine that we can start to collect incrementally all the expertise and knowledge in the world, and we put that on the network at scale, because sometimes biologists need the physicists, need the doctors and so on, knowledge and expertise. Let's AI to connect that.
Khai, I want to thank you for talking at the Khai Personal AI Summit yesterday. You gave us a small teaser about this talk. You've gone into a lot more detail here. And I've spoken with you for hours on this subject. I have to say, I still don't get it completely. So maybe you can explain, is there a set of Boolean type of logic, or what are the essential operators that exist in putting together a reasoning network?
So this is tiny, but so I would be happy to do some demo, outside of this, to show how the system solved, for example, lady or tiger, or how it managed this biological network things. But typically, each node, that called thinking node, as you know, in a regular neural network, just have a connection. That's it. This case, the thinking node can manage logical connection as well, and can propagate forward, backward, spontaneously, and it can encapsulate an internal process that can be anything else. So I'm interested, to talk with a hardware company, because the idea is we can build a reasoning processing unit network, where today you have internet, right? But internet is not smart at all, doesn't do any reasoning. What if we encapsulate all these different tasks beyond computer, whatever task, based on the connection and the logic then the system itself should be able to find the resource. And one thing I would like to dive deeper, and I think this is a good audience, is to do what I would call reasoning programming, or whatever the term that has to be defined, which means today when you program a function, you have to think about where it goes to the next function and how it called and so on, right? What if you just program the function without thinking how it's going to be used, but you just describe the context and the condition why it should be used, and you throw into this network all the functions in the world, then when you want to solve a problem, dynamically the program will be built and not in a static way. But we should have more gin tonics and different. So please, yeah, connect with me on LinkedIn. Just put scale so I remember. And we will have another event in San Diego, beginning of June. If you are happy to see you again. But yeah.
Hi, I was a little late, so I apologize if you covered this at the beginning to all of you. Could you help, is there a simple definition of what reasoning means in this whole AI world and context and whatnot?
Yeah. Very important question. This is the main issue in AI is because we use term that we used to use it before AI exists, and we have some clear we have some quite good understanding of what it is. And then when AI use this term, we just match this definition to AI, and then we expect that it does what we think it expects. So reasoning is about rational processing to have an outcome that you can justify. And when I say justify, I'm not talking about explainable AI, because explainable AI is about to explain a black box. But as a human, for example, if I try to explain something, right, is based on the level of concept that I use to generate this reasoning. So reasoning is precise. It's not probabilistic. It can be wrong, because based on the knowledge you have. But if your knowledge is solid, it allows you to have a certain output. And then when your knowledge is not very good, it allows you to question and get a better knowledge.
Yeah. I'm wondering, as I look at your drug discovery example, if you're boiling the ocean, like it seems like you're trying to solve a problem that maybe it requires reasoning and maybe it doesn't. And you're trying to make predictions on whether or not a molecule is going to be efficacious in a cellular context, but you're also requiring that you solve a billion equations per second. And then that's just one cell, as opposed to dealing with the entire organ or dealing with the entire body. And so I just wonder, why start with the biggest, hardest problem? Why not start with, say, hey, I know that this set of genes is going to be expressed in this particular chunk of organ. Can I make predictions? Like, how much information do I need to make a prediction? Do I need to have a gigantic model to do this? Or can I use like somewhere between like 100 numerical differential equations or whatever, right? Because that probably is, that won't work, we know that. And so between that and 40 billion things happening per second for just 40 cells, like it seems like you're jumping right to the end.
So it's totally fair question. The thing is, we already have positive result. We found target with our model. The second thing is, human, when we try to find a drug and so on, or target, what we do is we think about some pathway, and then, oh, by the way, no, this pathway connected, oh, but okay, this one too. So no, so the system does exactly the same thing, but 1,000 times bigger. This is one thing. The second thing is, it's why we are not focusing on the differential equation, because it's very limited for a number of things. we try to be the way that the scientist is doing, be able to overcome some lack of knowledge and so on by other way of thinking, abstraction, hypothesis, and maybe, but we do it 1,000 times the scale. Now, if you take something that you know very well and you solve it, it can be super accurate, but it can be totally wrong because the impact, as you know in biology, the feedback loop and so on, make it totally useless. So we think that it's better to have a broad image. Since a small approach already works with the scientists, let's make it a broad image of what's going on. We know that it's not perfect, but it's way, 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 way better than what the way human we are doing today. And it works, and we improve the model every 6 months. But totally fair thinking, yeah.
Hi, Dr. Pham. Thanks for giving your talk again. I looked up that doctors recently use MRIs to see thoughts in the brain so they can tell when you see ice cream. And I was wondering if it's possible to see when knowledge becomes, useful, or when you're doing reasoning in the mind. Because I think we can tell when we don't understand something, and then we can tell when we do understand something. So can you see that with an MRI?
Wow, I don't know, and I don't think so with the technology we have today, because the granularity that you are talking about is quite deep, and it challenged a concept that I tried to figure out for so many years, is what really mean understanding. Why you have this emotional feeling? Yes, I get it, right? We all have this feeling, but what is exactly that moment that trigger that? So already at the even psychological level, well, I have some guess. My guess is when we have a new concept and we are able to connect it with the existing concept that we have already, this is the aha moment. It's a very poor explanation of understanding, but it's what I can come up today. But yeah.
So we have maybe 2 or 3 minutes if there's any more questions. Here we go.
Thank you for the talk. It was great. And so the New England Journal of Medicine.
Sorry?
NEJM, the New England Journal of Medicine, now has a monthly journal devoted, that includes a significant AI component in it. So my question to you is, how do you think the average clinician will use the information you're suggesting we can obtain?
I'm sorry, can you
No,
talk louder?
So my question is, for patient management,
Yes.
to what extent do you expect this to be used? Because at the moment, even in the New England Journal, it's basically data, knowledge, and correlation that gets applied. And for most acute medicine, it's all you need. And it's the more complex and prevention that you are ascribing, that you say we need to be more aware of. And so I'm just interested in where do you see this particular tool being positioned?
Very important question, because my background is MD, so I care about the patient at the end of the day. A lot of study projects have been done on using patients' data to try to understand what's going on, to predict things. And this has driven to major bias. For example, one of the last publication is based on the fact that the system was predicting, how much urgent care or additional care this person need based on how much they would spend in the healthcare system, and it's totally ignore the minority population that don't have access to the healthcare and so on. So absolutely, in this kind of domain, reasoning can really help to get away from this kind of bias. The other thing that we would love to find partners and how to work on it is personalized medicine. I'm not talking about precision medicine, I'm talking about personalized medicine, which means we can take the gene expression data of the patients, generate the digital cell clones, and then scan the 10 different drugs that you should have. Let's suppose you have cancer, and see which one have a better chance of success. But even though you have a technology, then how to put that, on the market to be sustainable, find partners, and so on. But for the patients, you can use that at the individual level, but at the management level too, because you can exclude the bias as much you can.
Okay, and with that, I think we're at time. That was a fantastic question session, and it takes a fantastic talk to stimulate those questions. So can we give our speaker another hand?
Thank you very much.